Hello everybody and welcome back. We're up to question number 7 on the 2000 Euclid paper. So it's the grade 12 paper. We're up to question 7, so hopefully you have had a chance to take a look at it by clicking the link in the description below or otherwise obtaining a copy of the contest. It's always a good idea to try these things before you watch them be done or read solutions online. So, assuming you've given it a chance, let's dive in and take a look at it together. We're up to part A of question 7. That's where we're going to start. It's a light bulb question. A cube has edges of length n, where n is an integer. 3 faces, meeting at a corner, are painted red. The cube is then cut into n cubed smaller cubes of unit length. Okay. If exactly 125 of these cubes have no faces painted red, determine the value of n. Okay. So this is going to be a visualization question, a 3-dimensional visualization question. Can we picture in our heads a cube, and let's suppose it's sort of like a gridded cube, so we can clearly see that it's n on each side, length n on each side. Okay, and we try and mentally we pick a corner and we just look at that corner head on, and we paint those cubes red. Okay. We chop the whole thing up, and then we find we have 125 cubes that have no faces whatsoever painted red. Where are these faces going to be? Are they going to be located, sort of whereabouts are they located on the cube? Can we count them all in a meaningful way that relates back to the value of n? Because we're trying to determine the value of n. Okay? So it's a spatial reasoning question. And what we can do is we can draw well, my solution is going to involve drawing 2 pictures. So I'm going to draw a cube, and I'm going to be looking at the corner that I'm trying to sort of chop up. I'm going to be looking at that head on. So we have 1, 2, 3, 4 in this picture. Okay. So I paint this whole side red, I paint this whole side red because it's 3 faces meeting at a corner. The whole thing gets painted red. And then I chop it up. In this case, I'll have 64 cubes left over. Is 4 the answer for the side length of n? I don't know. But if I'm trying to think about what cubes won't have any paint on them, there'll be cubes that don't share any face with these 3 faces. So that's things like the cubes on the interior. The cubes at the very center, they don't touch any of the outside faces, so they'll definitely not have any paint on them. And there are a few other cubes that don't as well, and that's why we're just looking at the front view. Now, if we were to draw the back view, okay, looking at it maybe from below, okay, the red faces are on the sides that we can't see, and that's what makes this a visualization sort of question. So the red faces are the ones that we can't see. So this is completely, we've actually just oriented it in our hand, and we're looking at the exact opposite corner to the one where the red faces meet. Okay. Cubes still along the outside edge here are going to have red painted on them. Okay, and that's going to disqualify these cubes. Okay. Yeah, okay. So we're going to be able to discount these cubes, all the cubes along the outside. And what we're going to find is that we're left The cubes that aren't painted red at all, the cubes that are left over, they form a smaller cube at the back. Okay? And this makes sense to us once we realize it, because we are told that 125 of these cubes have no faces painted red. 125 is a cube. It's 5 cubes, so it's 5 by 5 by 5. And so when we realize, just from our visualization, from our little picture, that there's going to be a whole cube sort of tucked in at the back that is not painted red, then suddenly things start matching up. This smaller cube is going to be 5 by 5 by 5, and that gives us 125 cubes that aren't painted red. So 125, 5 cubed cubes aren't painted. This smaller cube must be 5 by 5 by 5. Okay? And we want to know what n is. N is the side length of the original cube. Well, if we just take a look here, and we'll use maybe green, the side lengths that become 5 are everything up to a tiny little buffer of size 1. So here we have 5, and then here we have 1, this sort of border of cubes that do touch the red faces. There's sort of a buffer layer and is the 5 by 5 by 5 plus an additional 1 sort of buffer layer of cubes that happen to have part of their faces red. So n is equal to 6. Okay? These three-dimensional sort of spatial reasoning questions can be quite tricky if you don't look at them in the right way, which is why I recommend that people bring props. For example, if I could have, I would have, back then I didn't have quite the collection I do, but I would have brought a prop like a Rubik's Cube, because you do find semi-often there are questions on these math contests that do involve having a grid, having a cube or a cuboid or a rectangular prism chopped up into unit cubes, and that's exactly the sort of pattern you see on a Rubik's Cube and the even bigger ones. So if I'd thought ahead, if I'd read this question a little bit, I might have brought out my 6 by 6 by 6 Rubik's Cube and been able to more visually display that for you guys. But we don't know ahead of time whether or not we're going to need a certain prop on a contest, and that's why I don't read these ahead of time and come out with a particular prop. But it's, as I say, the 3D reasoning questions can be quite tricky, so they're ones that you want to earmark and practice and practice and practice and see if you can find others online. I know particularly that's my weakness. You might have weaknesses in other areas, maybe probability or something like that. It's always a good idea to be able to identify the questions that you don't like, so they're usually the ones that you find really hard, and get as many of them as you can so that you get practiced with them, and then maybe they're not as scary. Okay, now we still have B part. Sure, we have n is 6 for A, but we still have B part. So we have an isosceles trapezoid, and that means that these two lengths, AB and CD, are the same length. They're given the length x here. So we have an isosceles trapezoid, and as I say, AB, CD are both equal to x. The area of the trapezoid is 80. Okay, so already we're starting to think, how do we figure out the area of a trapezoid? And there is a formula for that, sort of based off of parallelograms. The area of the trapezoid is 80, and the circle with center O and radius 4, so radius 4 to the tangent points here, is tangent to the 4 sides of the trapezoid. Determine the value of x. Okay. All right. So, we're given tangent points and a radius, and we're given an overall area. So we're actually going to be combining a number of things here. Let's draw ourselves a nice healthy picture. I'll draw the trapezoid first. No, let's draw the circle first. And we'll add the trapezoid in later, because it's easier to fake tangency points than it is to try and draw a circle in parameters. There we go, that's okay. I just can't seem to get this point of tangency here. Alright, so we have a center O, we have A, B, C, and D, and we want these values x. Okay, and we know we have a radius of 4. So, for example, we can drop these radii to the tangent points. And that'll be extremely helpful. Okay. Now, one thing that we can do is we could, for example, we noticed that we can label these tangent points as P, Q, R, and S. That way we can talk about them, because tangent points like these have a very, very nice property in that given two tangent points here, if we extend them to a common point, so on any circle, with a point P outside, here's a circle, here's a point P, any lines passing through P and also tangent to the circle and the distance from P to the point of tangency the same. So we have our point P out here. What this means is we have tangency points here, then these two lines have the same length. That's what the theorem tells us. And this is a common circle geometry result, but it means that SB, for example, is the same as BR. Okay, and RC is the same as CQ. And we can also get these points out here. And it turns out that by symmetry, we're also going to have QB is equal to BQ. Sorry, BP. And PA is equal to AS. Oh, and by similarity, sorry. Because the whole picture is symmetric, we could draw a line right down the middle, and it would be the same on one side as the other. We know that these lengths are actually going to be the same on one side as the other. So what we can do is match up common lengths, and by symmetry, SB is going to be equal to BR. We knew that is going to be equal to SA is going to be equal to AP. And the other one, RC is equal to CQ is equal to QB is equal to BP. Okay? So we really have sort of two lengths in here. And the interesting thing is that these two lengths, when added together, actually make up the length X. So why don't we give them names? So we'll let AP equal Y and PB equals Z. Okay? Well, then we have Y, 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 Z, 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 Z. Okay? So we have a whole bunch of information. We know that Y and plus Z is equal to X. Okay, so maybe it might just suffice to figure out what Y plus Z is. We can also see that A, B, C, D, AD is equal to 2Y, and BC is equal to 2Z. Now, why do I single these two out? Well, we're given one other piece of information to help us solve the question, and that is the area of the trapezoid. We haven't used that yet. We haven't even used that the radius is 4. All we've done is we found these points of tangency. Well, we didn't find them, but we drew them out, and we said, oh, point tangency theorem with a circle. We know that these lengths are the same, and we're going to give them names. That's all we've done so far. We haven't really used a whole lot of the information, so we still have yet to use the fact that the radius is 4, and the area of the trapezoid is 80. So how about we get on that area of the trapezoid right now? So, for any trapezoid, we have two lines parallel. To find the area of this trapezoid, that's going to be equal to 1/2 the area not just of this trapezoid, but what we do is we take a copy of it and we turn it 180 degrees and it matches up really nicely. And it forms a parallelogram. So it's 1/2 the area of a parallelogram. Okay, and this parallelogram has, if we have A, B, C, D, and a height h, then this parallelogram has height h and a base of D plus A. Okay? So the formula for the area of a trapezoid is 1/2 h a plus d. Okay? Same as the area of a parallelogram, but we're chopping it in half to make this trapezoid. And it really doesn't matter whether or not B or C are equal. All we need is A and D are parallel. Okay? So you can go on and use this, if you've never seen it before, to figure out areas of other trapezoids. So specifically for trapezoid ABCD, we know 80 is equal to 1/2 the height, which we'll call h, and 2y plus 2z. So how do we figure out the height? Well, the height is just going to be 2 times the radius. And we know that the radius is 4. Right? Because, and this is important, another result from sort of circle geometry is if you have a circle and you have a line tangent to it, if you extend a radius from the center to the point of tangency, this will turn out to be a 90-degree angle. Okay? So if you feel the need, you can actually write down that result, just as we wrote the previous result about points and the distance to the point of tangency for a common point P, that those lengths are constant. You could also write this result down to remind whoever is marking that you do know what you're talking about. But we can easily see that 2 copies of the radii, the diameter of our circle, is going to actually be the height that we need. Okay? And so this height here is going to be 2 times the radius 4, so it's going to be 8. Okay? So that means that 80 is 1/2 8 times 2. And what we can do is we can actually factor out the y plus z. So times 2 y plus z. Okay? So these two cancel each other out. And we're left with 8 times y plus z, but that's just x, which is the value we want. So x is going to be 80 over 8, which is 10. And that gives us the value of x. So we really had to use every single piece of information in this question. Okay? We had to know circle geometry. We certainly had to know a couple things about external points and tangencies and the way radii hit tangent points. Those are just little circle geometry facts we needed. We also needed to know how to compute the area of the trapezoid, because that was something we were given. So immediately, as soon as we see area of trapezoid, we need to start thinking, what is the formula? The same sort of thing happens in questions with triangles and area. We start thinking, what is the area of a triangle? What's the formula for that? And there's lots of area of triangle formulas, but there's really only the one area of a trapezoid formula. So we were pretty confident we knew what we were doing with that. And then we have to ask, why is the radius 4? And then we realize, oh, that gives us the height, which is something we need for our area of trapezoid. Okay? So lots of results we should know, and lots of pieces of information that we were given that we needed to tie together. And that gives us 7b, all nice and neat. And we're in the home stretch. 8, 9, 10, these are the hard questions, and we're going to see number 8 in the very next video. So thank you for watching, and I'll see you hopefully in the next time.